Hello everyone, my name is Kevin Abreu and I will be presenting my topic of short circuit calculations for class EE521, Power Flow or Power System Analysis by Professor Bose. And basically I'm going to be expanding on different and more advanced applications that can be seen at the research level for short circuit calculations. As I mentioned before, I will be focusing on short circuit calculations. Now we're going to be discussing and showing some different methodologies that are expanding on the field of these calculations for power systems. This will include a distributed generation system, or provide some level of emphasis of how fault currents can affect, or what things need to be considered for a DG system whenever a fault occurs. We're also going to be talking about coupling power lines under different voltage levels while calculating a power system. The effect of a short circuit fault on an inverter that is connected to a balanced or unbalanced feeders, ABCD parameters, among others. The main goal of this paper is to present different applications that can be implemented for more specific power flow problems and how short circuit calculations can be modified to obtain accurate current calculations that represent that system model specifically. So now we're going to go into something a little bit different. This part of the paper, I actually wanted to emphasize that different standards can be utilized to calculate for fault currents. And some of these standards actually do apply to distributed generation systems. In this case, wind farms. So different standards utilized to calculate short circuit currents and wind farms are mentioned below. One of them being the ANSI, which is the American standard. The IEC 60909 is the European standard, and the superposition method, which I think some of us have utilized before, due to how useful and practical it is by evaluating different parts of the system and then doing the summation of them. Specifically seen, and this is more of a commentary rather than part of the paper, but this is easily seen when performing sequence 0, plus sequence and minus sequence when calculating fault currents. And as we can probably, most of us have performed in our undergrad level degrees. So the standard definitions for these standards, and I think it is vital to, prior to bringing any expanded calculations, it is vital to define what we're actually talking about, or the different the different system standards that have been implemented depending on the region. For example, in Europe, the IEC 60909 standard is applicable to any power network regardless if radial or mesh, up to a voltage of 550 kV with a nominal operating frequency of 50 or 60. It's important to mention that we're highlighting this 50 over here because we're talking about the European standard, rather than 60 as it has been utilized in the US, 60 Hertz. The ANSI considers the simplified EX method, which basically the main goal is to simplify the electrical network to an equivalent R and X values, basically our resistance and reactance values as seen from the lines, from the feeders. And obviously the feeders are the ones connected to the fault. So these are going to be our R and X values, our resistance and reactance, as seen from the perspective of the fault. The ANSI standards neglects pre-fault loads, assuming loaded network conditions. So this is really useful because by neglecting these pre-fault loads, we're only focusing on the values or the impact of the fault itself. Now we also have our superposition method, which the superposition method yields a short circuit calculation that assumes steady state and non-decaying. This is really practical, as I mentioned before, because you're only taking a snapshot of the system in that moment in time, which makes it much easier to analyze and implement. So we're also gonna, after moving from this standards, we're gonna evaluate our short circuit calculations and inverter applications. Currently, distributed generation applications have become more prominent in the market. Three-phase distributed generators can implement the use of inverters to couple the power grid to the generation system or transform AC to DC or vice versa. When the terminal voltage of an distributed generation, and for reference, IIDG, it's making reference to the inverters of the distributed generation system. So basically, when the terminal voltage drops after a grid fault, the output current of the inverter increases drastically, and sometimes even dramatically. It can actually be potentially dangerous for the health of the system. It can be detrimental to the health of the system if there's no protection system. Protection systems implemented to reduce the impact of that fault current. So the transient simulation and physical experimentation help explain the short circuit behavior of distributed generation inverters, but are unable to analytically calculate the short circuit current. So as we can see right here, this is a example or an image that might be really familiar with some other people in the class. And basically, this currents right here for the positive sequence and the negative sequence, they're taking into consideration the power, the reactive and real power, but they're also taking into consideration the U's. And the U's actually represent the voltage seen across the inverters, which is what we're going to have here and here, for example. So this equation right here, it is useful. It's actually pretty easy to understand after you spend a little bit of time analyzing it. It is useful for calculating fault currents that are gonna be caused by the inverters whenever a fault actually occurs, because they're gonna be outputting more current into the system, injecting more current into the system. So the distributed voltage control and short circuit analysis, the distribution management system is critical for regulating voltage control. To do this, step voltage regulators are implemented along with reactive power support from control, shunt capacitors, and distributed generators. Some of these distributed generators can be photovoltaic or wind energy conversion systems. This method aims to calculate the voltage and reactive power sensitivities from the Jacobian matrix of a grid power flow. This method is only suited for fixed load or offline optimization. In order to adjust it for online optimization, the Jacobian matrix must be updated after every sampling. The method consists of utilizing A, B, C, D parameters, which are constant. And this is really important to mention because by saying that they're constant, unlike the Jacobian, which requires an inverse of the Jacobian, every time that you update the voltages and the angles, these values are actually fixed. So once you have your system set up, your matrix set up, the ABCD matrix, you can continue utilizing them not only for one specific fault current, but actually for different ones. Like for example, three-phase fault current, a line-to-line fault current, double line to ground fault current, and single line to ground fault current. The only thing that needs to be updated is the local voltage nodes. And these are actually pretty straightforward to calculate. As soon as you have the value, you update it, and that way you have your new voltages for the next set of result sweeping, or before your next iteration. So going into the next slide, the main steps to calculate faults for a distribution voltage control. So basically, there's going to be a new method for calculating voltage sensitivity to active or reactive power injection in unbalanced distribution feeders utilizing ABCD parameters. The online updating, that means when the system is actually working, it's performing, it's a live system, live energized system. The online updating of sensitivity is straightforward and is suitable for online calculation. A new method for calculating voltage sensitivity to the step voltage regulator taps. It's also going to involve a new sensitivity-based method for online voltage optimization and online coordination between reactive power sources and step voltage regulators. And it's going to involve a new method for calculating short circuit currents in unbalanced distribution feeders based on cascaded ABC parameters. And this here, number 4, is what we're actually going to try to focus on. So ABCD matrices, some of us potentially might have been able to see this in our undergrads, maybe at some master level degree classes related to power engineering. But basically, we're going to have two equations, which is going to be Vs and Is. And we're going to say that Vs and Is are basically voltage sent and current sent are going to equal A VR, where the R stands for receive. So basically our voltage sent is going to be equal to the A coefficient multiplied by the voltage received plus the B coefficient multiplied by the current received. And the same thing is going to apply to the Is, with the only exception that we're going to utilize C and D rather than A and B, as seen in the case of the voltage sent. So voltage sent, once again, equals A times voltage received plus B times current received, and Is is going to equal C times voltage received plus D times current received. And by using these values right here, these coefficients, we can actually put them in a matrix by themselves. And this is what we call the actual ABCD matrix, because we're taking these coefficients. These coefficients basically represent the actual power system, the actual power grid. As we can see here, A, B, C, and D. And like for example, here we have our substation, right? And we can see that the specific parameters for our coefficients from here to here are this A, B, C, and D. But if we actually want to measure from I to J rather than from 0 to I, it's going to be Aij, Bij, Cij, Dij. And we can do the same thing for the whole system, from 0 to J, Aj, Bj, Cj, and Dj. And this represents the system as I mentioned before. So basically, when performing short circuit faults with ABCD parameters, the first calculation method will be done for three-phase faults. So we're going to start with the simplest ones, or the most straightforward one. As seen during the class model, three-phase short circuit currents are given by VI equals CFII, where VI is the voltage of interest, II is the current of interest, and CF is basically the impedance of the fault. Where the fault impedance matrix CF equals the diagonal of CFA, CFB, and CFC, where A, B, and C are basically our phases, phase A, phase B, phase C. This is then utilized to calculate short circuit currents for three-phase short circuits, as given by II equals AI, so basically the current multiplied by the coefficient A, multiplied by CF, which is our fault impedance, plus BI, which is once again our current multiplied by the coefficient B. This is all raised to the power of -1 multiplied by V0. So basically it's going to be our coefficients right here, raised to the power of -1 multiplied by V0. And I0 is going to be CI VI plus DI II. So basically our coefficients, once again, multiplied by the voltage VI and the current II. And this gives our I0, or I0 being the fault current. Secondly, the single line to ground short circuit current has the following conditions. We're going to assume that the fault is at phase A, but it can be done for phase B, phase C. So basically, we are going to have our BIA, which is going to stand, in this case, for phase A. So this is basically like we're mentioning here. Assume fault at phase A. So VIA, or VI for phase A, equals the fault impedance at phase A multiplied by the current at phase A, once again. So that gives the voltage. And we're also going to assume that IIB and IIC are going to equal 0. So by having these values, calculating the actual current is pretty straightforward. And once again, the single line to ground short circuit current is another really easy to calculate current, which is why it's pretty brief by itself. Now we're proceeding to the line-to-line fault, and the line-to-line fault is actually going to have a special equation. Our DT parameters actually are obtained from this equation below, where we're utilizing coefficient CI, coefficient DI, and once again multiplied by coefficient CI. And this first CI that we have right here is multiplied by the fault impedance. So this is our coefficient factor to represent the model for a line-to-line fault. And we also, if we take a look at the IO equation, it equals dTy. So y will equal to the transpose matrix of the current in phase A, the voltage in phase A, and the voltage in phase C. And these are basically the phases that are being affected. Remember, this is a line-to-line fault, so we're going to be utilizing phase A and phase C in order to obtain our short circuit calculation. As soon as we have dt and y, we plug those numbers in, and they're going to yield our IO, which equals dty. And once again, all these values, remember, we're not inverting any Jacobian, so it is really efficient. This is basically algebra that we're performing at this point. And we just continue to iterate over and over, and we continue to obtain new voltage values and current values until our system stabilizes. And once again, using the same equations as we see right here, IO equals dty for the fault current, we can do the same thing for the double line to ground, which is going to be y equals the current in phase A, the current in phase B, because we have a double line to ground now. And we're also going to have the voltage in phase C. And we transpose that, plug it in our y value, multiply by dt, and that equals our I0. So the benefits of ABCD short circuit calculations are going to be that the main benefits of using these results or this process is that the results are really easy to obtain only by updating the coefficients. When we have our ABCD matrix set up, we plug those values into the previous equations that we saw, and we avoid matrix inversion, which is a costly process for computation purposes. Similarly, it benefits from voltage regulation. By forcing a hard limit on the buses, each new sampling as the new coefficients become calculated will refresh the system values, preventing from the voltages to fall outside of preset boundaries. So every time that we do, if we impose voltage limitations in the system, they're actually gonna be, by forcing these calculations, we're actually gonna stay within those boundaries after we update our values every single iteration. The calculation of short circuit current for partial coupling lines under different voltage levels. This is gonna be our last topic for the paper, and this is another application. This one is actually pretty interesting because what we're doing here is that this method will consist of analyzing short circuit calculations on power lines under different voltage levels. This becomes complicated when taking into consideration the mutual impedances on sequence 0. Therefore, by isolating these zero components, they can be transformed by comparing the relationship between sequence voltages and sequence currents. The biggest impact to short circuit calculation occurs from partial coupling. By having different voltage levels in the line grid, the traditional positive and negative sequences are examined. However, the mutual impedance of zero sequence lines must be taken into consideration prior to performing any calculation. So basically, we're trying to account for those different sequence 0 components. Plus sequence and minus sequence are actually going to remain the same. And this is mentioned right here. That is, positive and negative sequences are not modified, but sequence 0 is really affected as we're trying to analyze these components separately. Imagine an easy way to see this is that we're performing superposition for the different sequence zeros, and by obtaining the summation of the sequence zeros, we actually obtain the actual result that simulates our model. So the changes to sequence 0 are pretty brief. For sequence 0, the system will be decoupled into two zero sequences, sequence 01 and sequence 02, which is represented by this system right here. And this is a graphic representation of what's actually going to happen. Once again, 01 and 02, this is more of a graphic representation that it helps us to allows us to see what's going on. So basically we have two lines. Our lines are going to have different voltage levels, and by analyzing these different voltage levels, we perform our zero components, right? We obtain the zero component for line 1, and we obtain our zero component for line 2 separately. Once again, these two set of lines have different voltage levels. So if you were to perform zero sequence, after you obtain your plus sequence and your minus sequence, you're going to notice that sequence 0 is going to be entirely different. This is why you're doing something similar to a superpositioning of line 1 and line 2 in order to obtain the whole sequence 0 of the system. And after you obtain that whole sequence 0, that's how you can calculate your short circuit current. What we want to emphasize out of here is that by performing separate sequence zeros, that is, in this case 01, 02, because we're assuming we only have two line system with different voltage levels. By doing this, we can actually do the summation. So if we go into the second line, we're going to see that our impedance of the sequence 0 is going to equal the voltage of IO, IO being the fault current. So this is only a designator. We're only talking about voltage here, divided by the fault current. And this is going to give us the impedance of the fault current in sequence 0. So by doing this, we can actually tell that for any amount of lines, which is going to equal different sequence zeros. So in this case, we only have 2, but it can be sequence 01, sequence 02, sequence 03, and etc. We will be able to represent a circuit taking into consideration the different voltage levels across the lines, and it can be any amount of lines. This is called as the composite sequence, because you're basically taking the summation of each separate sequence and combining it into one composite equivalent. And we want to end it up with a conclusion. Conclusion is going to be the following. Short circuit analysis is a critical tool for power flow analysis. Any power grid can be exposed to a short circuit fault under different conditions. First, topics such as different methodologies for solving short circuit problems were discussed. Here we mention our different standards, the ANSI standard, the European standard, which is the IEC 6909, and the superposition method that we have seen in our classes. These methodologies are actually utilized to calculate the short circuit current a wind farm can potentially see, and they all agree that by having the final calculation, these were the results, by having the final calculation from any of these standards, you're actually obtaining a valid short circuit current that will allow you as a design engineer to know this is your limit, this is going to be your fault current if you were to have fault, or this is the protection that you're going to require for your system. Secondly, the impact of a short circuit fault was analyzed for the case of power inverter applications in balanced and unbalanced feeders. In balanced feeders, the tripping mechanism of different generators behaves like a move cascading sequence. What we saw was that whenever we have an unbalanced system, the tripping mechanism is going to be really rapid and sudden, and this is basically because of the high level of the magnitude, which causes the breaker to trip almost instantaneously. But it is really important to mention that this high magnitude is actually caused by the inverter application. So definitely knowing what calculating or designing for that short circuit current is vital in order to utilize the correct power protection system. Third, distributed voltage controls utilizing ABCD parameters allow the user to quickly calculate faults by utilizing parameters that represent the sent and received voltages and currents. And as we saw, by using your coefficients and updating your voltages, it's really easy to calculate any of the faults without having or requiring the inversion of a Jacobi matrix. And finally, coupling lines with different voltage levels can be accomplished via calculating equivalent sequence zeros and obtaining the superposition sum of all line systems. So if you want to calculate the fault current for one system, and it involves different lines, different set of lines with different voltages, by obtaining the superposition summation of the sequence zero components, you can actually obtain the equivalent circuit, and from there you can actually calculate your I0 or your fault current as we have done before. I hope everyone has appreciated and enjoyed this presentation. It's a lot of material, but it shows you that there are many different applications that can be implemented for calculating short circuit currents. Thank you.